Hey everybody, Thrasher here. We're talking about center of mass. That's how we're wrapping up this relatively small sequence of videos related to momentum. Center of mass can actually be used in a wide variety of physics topics. We'll see it again later when we talk about rotation and torque, but the first time to really understand center of mass is actually after you understand the idea of conservation of momentum. And since we've done that in the last video, now it's time to first introduce this idea. Now, before I actually even talk about center of mass, we have to make sure we understand how things move. And motion, well, we've always kind of just looked at things happening off to the side from us, meaning we've seen a car driving down the road, or we watch a ball being thrown through the air. Depending on your reference frame, however, you might perceive motion slightly differently. And there's no incorrect way, or there's no way that's more correct. Here's what I mean. Let's say we're inside of a train. That's what this diagram here is representing. We're inside of a train. If we were just sitting still in a chair, we would probably say something like, I'm just inside the chair on this train. My velocity is 0. I'm just sitting. If we saw somebody walking down the hallway of the train, well, okay, they're probably not moving too fast. Maybe 5 ms, still too fast to be walking, but, they're just moving down the train. However, let's say we were actually on the outside of the train. In this scenario, we're on the outside of the train now. If the train was moving down the tracks at 30 meters per second, we wouldn't say that this person here, this individual sitting, we wouldn't say that they're at rest. We would say they're moving with the train at 30 ms. And this person, well, inside the train, they were moving at 5. Now we would see them moving with the train, that's 30, plus the 5 they had before. Is it wrong to say that this person is moving at 30 meters per second? Or is it wrong to say they're moving at 0? Well, neither is wrong. Both is correct. It's just relative. Okay, both of these can be accurate. Both of these, in fact, are accurate as long as you're aware of what your reference frame is. Normally, our kind of typical reference frame has been like this, but either way is acceptable. So this kind of nuance can be important when we're understanding the center of mass and how it may deal with or may interact with or affect the motion of objects, okay? Now, what is center of mass? First of all, I want to give you another term that's similar. Technically, it's a slight difference, but we're not really going to get into it. It's not really relevant for the physics that we're doing in this AP Physics 1 focus sequence. And that is center of mass and center of gravity can often be used interchangeably, okay? I hit pause and I moved one of those images because I noticed my head was right on top of it. But what is this idea of center of mass? The basic definition. It's an object's, average. It's where the mass is kind of concentrated, where the average location of the mass of an object is. Okay? Easy examples, think of some basic geometric objects. Like imagine I have this square or this cube, let's say. Let's say it's, pretty uniform. It's not made out of like different types of material, just one type of material. Its geometric average is right at the center. And if its mass is evenly distributed, its mass has an average location of right smack dab in the middle. Okay, that's what we would call the center of mass. Again, maybe you could say the center of gravity, kind of interchangeable. Likewise, if it's a triangle or a cylinder or a sphere or a circular little plate, the average location geometrically is in the center. And if it's a uniform kind of shape, a uniform material, the average mass is located in the center. To be honest, we've been using this every single time we've been drawing free body diagrams of objects. It hasn't really been relevant, but that little dot that we've been drawing, that represents the center of mass for an object. And 99% of the time, especially in AP Physics 1, all right, that center of mass is just going to be in the middle of the object. But not always. If you have objects that are of different kind of shapes and sizes, like a hammer. I have this desk toy in my own classroom. Okay, it has all different shapes. The location, and it is a location, the center, where we can kind of simplify the mass of the object, it's a helpful hint, where the object balances. If you take this little toy that I have in my classroom, it's designed to balance at the beak. Right here is that object's center of mass. If you take a hammer, if you try and balance a hammer on your fingertip, it balances right here. That's the hammer's center of mass. Okay, it's also kind of a little parlor trick you could do. Find any object, whether it's uniform or shape or not, try and find where it's balancing, and bam, you found the center of mass. It just represents, at the most basic definition, where the mass of an object can be simplified to exist, where it's kind of concentrated, its average location, okay? So for a single object, it's either just going to be right smack in its center, if it's geometrically and uniformly created. Even if it's kind of roughly shaped, it's just where the object is balancing. However, you can also look at the center of mass for a system of objects, okay? Here I have two different objects, two masses, maybe these are two different metal spheres, both mass m. Where would you say for this system, remember what systems are? Just the things I'm looking at. For this system, where is their center of mass located? Now, it's a little tricky. The center of mass doesn't actually have to be where there is an object, all right? If these two objects are uniform, their center is going to be, well, it's going to be in the center of, well, where they're located. It's going to be in the middle of them. Maybe a way to help you think about it, imagine there was like a, I don't know, a plastic rod or a metal rod kind of connecting them. Well, again, that geometric average or that center where it would balance, that would be right here. A little weird because that's not actually where either of the objects are, but that's where the geometric average is. There's mass over here, there's mass over here. The average is right smack in the middle. How about another example? If I show you this one right here. Ooh, 1 second, please. There we go. I had to slide that diagram over. Sorry, my head was in the way again. Now I have an object that's significantly more massive than the other. Where would its center of mass be for this system now? What would you think? It's going to be right here. Again, they're not actually where the objects are located. There's more mass on this left side. So where is the average amount of mass? Well, closer here to the left where that bigger mass is. Again, imagine you had some little plastic rod or something going in between. Where would it balance? Roughly around here. Okay, so that center of mass can also be applied to systems. And again, it's kind of where the average of those masses are located. All right. Now, here's our key idea and why this relates to momentum and conservation of momentum. If the momentum of a system is conserved, remember, we had a lot of collisions taking place in the last video and the last few homework assignments, if you're in my own class, but if the momentum of a system is conserved, if there's no outside forces outside of my system, well, what's the key takeaway? What do you need to know for the sake of the AP Physics 1 exam? It's that the velocity of the center of mass for that system remains constant. Again, I'll say that again. That center of mass, that average, it could either be at rest. I'll show you a demo in a moment where it could be moving. But whatever that motion is, whether it's staying at rest or even if it's moving, that motion is constant if momentum is conserved, if there's no outside net external forces. Okay, so the velocity of the center of mass can either be at rest or have some constant velocity, some constant speed. Let's take a look at what this means because my other pictures were just stagnant. They were just stationary. Here I have some ball, I have some mass, and it's moving. The X represents the center of mass of this object. Now, it's probably not difficult to understand that if it's moving, well, it's still this uniform disk, this uniform sphere. Where is the center of mass? Well, it's in the center, and it's going to be moving with the center of the object. Again, unless you had some object of like different densities in different locations, it's going to be in its just geometric center. And now it's moving, and notice there's no outside forces, so that motion is constant. What's a little weirder is that it's true, sorry, I gotta reset. It's true even if you have multiple objects, and even if there are collisions taking place. So here I have two objects. Now they have different velocities and they have different masses. This pink sphere is having a larger mass. So where is its average center of mass for the whole system? Just like we saw before, it's kind of shifted more towards that heavier object. Pretend these things were connected by a rod. Where would it balance? Well, right about here. This is where the center of mass is. Now when I hit play, I'm going to have this in slow motion. The center of mass is moving. And it's moving at a constant velocity even after the collision takes place. Because remember, that collision, that's not a net external force. Momentum is still conserved. So the velocity, that speed of the center of mass, it started out going to the left. It, in fact, continues going to the left even after the collision. That's hard to tell. And in fact, your eyes kind of want to deceive you when you do this. What I recommend, I'm going to hit this at normal speed. Take your finger, literally, if you're watching this on the TV or on your laptop, put your finger right next to where it's located and move your finger along with this center of mass. And you'll notice that while it's moving slowly, it continues moving in that same way even before and after. Even though there's a collision. Since the momentum is conserved, the velocity of that center of mass is constant. We reset now with an inelastic collision. I'm going to hit slow motion. So again, trace that with your finger. It's slowly moving to the left, 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 slowly moving. It doesn't change its motion. The velocity of the center of mass is constant since the momentum of my system was conserved. That's one of the big ideas. The velocity of that center of mass is staying constant, okay? There's another idea. So that first idea, very important for College Board and the AP exam. There's another important idea, kind of an addendum to that first one, okay? This center of mass, well, remember, it's kind of what we've been using for those free body diagrams. Even when you have some oddly shaped object, that center of mass, its motion, well, that's the motion of projectiles, second law, accelerations, momentum collisions, energy, converting from kinetic to gravitational potential energy. You can use center of mass kind of to simplify otherwise complicated objects. Here's what I mean. Let's say you take a wrench, or I always imagine this with like an axe, right? Axes or wrenches, they're really top heavy. They have a lot of mass over here, not as much mass over here. So their center of mass is right where this arrow is. Now imagine you took that wrench and you tomahawked it. You chucked it across the room. It has some pretty complicated motion, right? The head of the wrench is kind of going around and around and around and around. But the center of mass, if you could trace it, it would have that characteristic projectile motion path. Same thing with like a diver right here. You know, you have arms and legs that are flailing all about. But when you go off a diving board, your center of mass, which is right about where your belly button is, conveniently, your center of mass still obeys projectile motion. And in fact, when we're doing problems and we say, you know, there's somebody jumping off of a diving board, somebody or some other weirdly shaped object is fired through the air, we can use all of our physics. Even though like your arm might be flailing about, all of our physics that we've learned, technically it's been applying to the center of mass for the object. Which means if you see or you encounter some oddly shaped object or something with different parts moving in different directions, it's almost a key word. If you see center of mass in the problem, it just means you're going to approach things just like you would any normal kind of shaped object with projectile motion, with conservation of momentum. That idea that I mentioned before, that the velocity of that center of mass is staying the same. I have another visual to show you. This video right here is going to show something like that wrench, or if you had a hatchet or an axe and you just chucked it across the room. Here I have a really complicated object. I have these 3 different spheres. They're attached, and they're just going to be chucked as a projectile. But oh my gosh, if you focus on the red mass or the white mass, look how complicated this motion looks. That white sphere is moving in all different ways. That yellow sphere is moving. These different circles, they're not even circles. They're all elongated. If you saw this on the AP exam, and to be honest, you might first curse the name of your teacher. You might curse my name after you watched all these videos. You'd be like, what the heck, Thrasher? I haven't seen this kind of motion. But the AP exam might say, calculate, I don't know, the acceleration, or what is the acceleration of the center of mass. The center of mass is right in the middle. That's this red sphere. Watch the red sphere. It has that center of mass is that classic parabola. That is accelerating at 9.8 meters per second squared downwards. Yeah, the white one and the yellow one, that might have more complicated motion, but the center of mass, all that same physics. So sometimes College Board and sometimes your teacher might give you some object that's really complicated with springs and different pieces. It's not all uniform. But if you see the words center of mass in the question, it's almost like you could take a deep breath and be like, they're trying to make things more confusing than they are. It's asking about center of mass. So just go back to the basic equations, the basic physics that you're already used to. All right? Just a little bit more. I have a sample problem right here. I scooched it over to the left again to make room. Okay, it says a student is on the canoe. They're standing at one end. So here's the person standing at the canoe over there on one end. Okay, they walk to the other end. If we ignore resistive forces from the water, why must the canoe move backwards, okay? Now, there's a few ways you could approach this. One, if the person is applying a force on the canoe is applying a force back on the person, that canoe is probably moving. There's a conservation of momentum thing going on here, right? Momentum needs to be conserved. If there's no net force, momentum needs to be the same at the beginning and the end. There's also the idea of that first idea we talked about. The velocity, the motion of the center of mass for an object is constant if there's no outside forces. So if there's no outside forces, the velocity of the center of mass, and sometimes you might see it like this, the velocity of the system's center of mass needs to be constant. Well, at first, if I'm just standing on a canoe at rest on the water, what is the velocity of my center of mass? Nothing's moving right here. So the velocity should be 0. That means even after there's movement taking place, since this is all internal, momentum is conserved, there's no outside forces, the velocity of the center of mass needs to remain at 0. It needs to remain that amount. Okay, where is the center of mass? Well, if it was just the canoe, the center of mass would be like right here, right smack in the middle, but there's a person, okay? The person has mass, so where is the average mass? This picture actually already has it located. They have it already diagrammed right here. Okay, the average location, because there's this person on the left, is over here. So if then the person starts moving to the right, well, the velocity of that center of mass was 0. What does that mean in real life? It means that that center of mass can't start moving. It needs to stay in the same location. So, since it started at rest, well, it has to stay right here. The water is right here, and then the water, it's right here, but it can't move because it was at 0 in the beginning. It has to stay at 0. So if the person started walking, the canoe has to shift backwards the other way, always keeping the location of that center of mass at rest. So you might see problems where it says, you have this rocket and then there's this other part attached. They blow apart. What is true about the velocity of the center of mass? Oh my gosh, it seems complicated. It seems confusing. But you see that term. You see center of mass. Take a deep breath. This is my test-taking tip. It's probably easier than it seems. Okay? If you can say, well, this whole thing started at 0, or the whole thing was moving to the right at some velocity, so therefore the center of mass was moving to the right. If then there was some confusing breakup going on, well, if it's asking about the velocity of the center of mass, it's the same as it was before, because it doesn't change if the momentum of the system is conserved. As always, weird to encounter at first, but once you see a couple of them, as long as you remember that key word, if a question talks about center of mass, these actually end up often being easier problems because you just it's simplified and that velocity, whatever speed it might have, it's staying constant. Okay? I know there was a lot to unpack in this video. Thanks a lot for watching. That's it. I'm signing off. Take care.